This video will cover section 5.2 of the class Math 1324. The title of this section is Compound Interest and is the second section of chapter 5, which is dedicated to finance or formulas that are used in finance. So here, the previous section we discussed the simple interest, and I did mention that one is comparable to a linear function. And it is comparable to a linear function because you could see here for the first 3 years there is a constant rate of change, and so every year the account is earning $50. So it could be like a slope being $50 for every year. Now when we discuss compound interest, that one could be compared to an exponential function. And if you look at the first 3 years also of the loan, for the first year, the increase was $50, which happens to be the same as simple interest. But that will only occur during the first year of the loan. Now, for the second year, the interest earned is a little bit more, $52.50. And then for the third year, the money earned is $55.13. So you could see that every year this is increasing, and it's not a constant rate of change like we could say with a linear function. So the reason for that is that simple interest, you put your $1,000 in and the account only earns 5% for every year out of the initial value invested, or the present value like we were calling it in section 5.1. With a compound interest, you start with your money invested, the principal or the present value, and you earned 5%, but then what happens for the second year, that new balance becomes your new present value, and you earn 5% from there. And so with that added, the $52.50 added to that present value, you get a new present value of $1102.50. Now that becomes your new present value when you calculate the interest. So this is something similar to earning interest over your interest. And because of that, the future value on this type of accounts increases exponentially, because for every year you will be earning more and more and more. So for our first example, we're going to have a $7,000 deposited into a savings account that pays 4% interest. And here, this is important, compounded annually. So the fact that it says annually, that will make our number of compounding periods. And for that, let's introduce this variable to number of compounding periods. For the first two problems, the number of compounding periods we will be using is 1. And the reason I know that is because the word annually. Then how much money is in the account after 9 years? So in this case, we could say that T will be 9. It's already in years, so we don't need a fraction for that. And then we could also say that the rate is 0.04 and our present value is 7,000. So for the first year, we could have 7,000 plus 4% of 7,000 or like we should say 7,000 plus 0.04 times 7,000, like if we convert this percentage into a decimal. And if we factor out 7,000 here, because they both have it, right, both terms. So if we factor it out, we will get, if we factor 7,000 from here, we get 1. And if we factor 7,000 from here, we will get 0.04. Now, if we add what's inside the parentheses, we will get 1.04. And so if we multiply that 7,000 times 1.04, we will obtain $7,571 with 20 cents. Now, so if we continue to do that, now let's assume that our new present value will be $7,571 with 20 cents. And from there, we want to add 4%, but not of 7,000, of the new balance. And so with that said, it will be our new balance Okay, actually, I made a little mistake, not a big deal. The answer for this one was 7,280. So then here, that was after the first year. So for this one here, we should be using that, 7,280. Okay, you'll see why I made that mistake. That's actually the answer to this question. And we will use the same idea that we used here, that every year it is earning that much, 1.04. And so after that, so after the second year, the new present value will be 7,571 with 20 cents. So now, of course, we could keep doing that over and over and over again, and every year that we do it, the formula will change. So if we do that for 9 years, because we're talking about t equals 9, basically what we're doing is multiplying by this factor, 1.04, to the power 9. So to make this short, we could take the initial present value, 7,000, and multiply it by 1.04 to the power 9, because we're going to do that for 9 years. And so if we were to do that, the answer will be 9,963 with 18 cents. And so the book explains something such as you start with 7,000, and then after the first year is 7,000 times 1.04, which we did here. Then the next year, because we multiply by that 1.04 again, the idea is that it's 7,000 times 1.04 to the power 2. For the next year, it will be 7,000 times 1.04 to the power 3, and so on, until you get to the 9th year. And so that would be 1.04 to the power 8. I'm sorry, not 8, but 9. Okay, so if we go back to the formula here, that is what we will see. Now here, I want to warn you that we are using n as the number of compounding periods. But I would like for you to keep in mind that it's m what we're going to use for the number of compounding periods. Why? Well, because later on, we're going to need to know that n is equal to m times t. T is the number of years, and M will be the number of compounding periods. For right now, it's annually, so we consider that M equal to 1, and that is why the book is saying that N is equal to M, only when the number of compounding periods is 1. So, to answer this formula now, we do have this table of values, and so it does show us what will happen year after year after year. So you could see it's comparing simple and compounded interest. Keep in mind that the formula for simple interest is present value times 1 plus RT, and the formula for compound interest, it will be present value times 1 plus R to the power N. So, for this question, we need to find the compound amount. And I'm going to erase certain things here. And we need for 6 years for $1,000. And if this was compounded annually. So, present value is 1,000. Time is 6 for 6 years. R will be 0.0831, and M or N is 1. So we will be using the formula. Future value is equal to the present value, parentheses 1 plus I over N. And right now here, let's go back to this box and define I as R over M. You know that R is the rate and M is equal to the number of compounded periods. But anytime we talk about compounded annually, I will be the rate divided by M, so it will be 0.0831 divided by 1. So in this case, I will be the same as R, only when it's compounded annually. So to finish this problem, the future value will be the $1,000 multiplied by 1 plus 0.0831, and we want the value after 6 years, so the exponent will be a 6. Now you could also enter this on your calculator as this: 1,000 parentheses 1.0831 to the power 6. And so if you enter this correctly, you will obtain $1,614 with 40 cents. Now to find the amount of interest earned, we could take the future value minus the present value. So this will be 1614.40 minus 1,000, and that will equal to 614 with 40 cents. And so that will be the answer for part B.